In this movie, I want to look at enantiomers in more detail, some of the more specific details about their properties, because this is such an important class of isomers. So again, these are stereoisomers that happen to be mirror images of each other. So let's continue to absorb that definition. So stereoisomers that are mirror images of each other. Okay, so they, in most cases, they have mostly identical properties. And that would be melting point, boiling point, color, that sort of thing. But Calvin, I'm recording a lecture right now. I need you to go. Very good, very good. Okay, thank you. Okay, so for the most part, these things have very similar properties, but they differ in how they interact with other chiral objects. And that's where we really want to make sure that we understand enantiomers in more detail. Okay, so they differ in how they interact with other chiral objects. Now, an example of chiral objects, we've talked a lot about molecules and left-handed scissors, right-handed scissors, types of shoes, that sort of thing are chiral objects that enantiomers could interact with that are different. But another example is more of a physical example, and it's sort of weird, but it's important, and that's plane polarized light. Okay, all right. I can already feel the eyebrows is kind of a little concerned about this already. Plane polarized light. So what we're doing is we're going to take a light bulb, and we are going to turn it on. And when we turn it on, we get radiation. That's why we build light bulbs. Radiation. So I've got these sort of waves of light drawn. And we see the light. If we look at the light, we could even draw like a Newman projection. So here's my Newman eye. So what we see is as follows. Well, we kind of see light going in all directions. Call this omni or multi-directional light. It's bright, you know, right? There's just so many light waves. So maybe what we could do instead is add a polarizing lens. And in fact, that's what we do in many times, right? If the light is too bright, we add a polarizing lens. It's a skinnier light bulb. Few light waves. I should draw this better. I'm going to do a better job of this. Okay. So if we put this in sunglasses, we would call it a polarizing lens, but in general, it's a polarizing filter because it reduces the amount of light. So what we see as we look through the polarizing lens or polarizing filter in our sunglasses is less light, and it's a little bit easier to digest, right? And so you could drive a little safely or more safely or something. What we're actually seeing is light that's kind of moving in only one plane. So we have a single plane of light. So it's dimmer, it's a little bit easier to digest. But something that's very interesting is that light is chiral. Now I'm not going to go into the physical details of this, but the light, plane polarized light, is chiral. And you know, what's going to happen is I would just have to do a much longer explanation of light to really get at why it's chiral. But suffice it to say, we know how to generate plane polarized light with a polarizing filter. But plane polarized light, and I like thinking about it straight up and straight down. It really helps us to understand what's happening when we interact with enantiomers. But plane polarized light is chiral and interacts oppositely with enantiomers. So it turns out that when plane polarized light comes into contact with a chiral molecule, the light is going to be rotated. Specifically, it's rotated in opposite directions. Huh. Well, why is that so helpful? Oh, here's what's going to happen. Let's say we take plane polarized light. We had our initial light source, and then we passed it by a filter. Now we have light that's pointing kind of straight up and straight down. I'm going to pass this through a sample chamber that has this molecule. We are then going to see rotated light. Now, if the original light was pointing straight up and straight down, okay, so I'm just going to draw like the center of these light arrows. And sorry, those are a little bit sloppy at the original. Now what's going to happen is we're going to see the light waves kind of turned a little bit. And if we measured the angle of the turn, it would be about 23.1 degrees counterclockwise. 23 degrees counterclockwise. So what happened is that our chiral object, the plane polarized light, interacted with the chiral object, which was a molecule, and it was rotated. It rotated the direction that the light was propagating. This case, and for this particular molecule, is 23.1 degrees counterclockwise. That would change for different molecules, and sometimes that change can be predicted. So this phenomenon is called the optical rotation of a chiral or by a chiral molecule. So this is just another example of a chiral object interacting differently with another chiral object. Now, when I say different, I mean if we did the exact same experiment and we used the enantiomer of the above molecule. So the enantiomer is going to be the mirror image structure, or the structure drawn in its original depiction, but flipping all of the wedges and dashes. Those are the same. Okay, again, enantiomers are mirror images, but if you don't want to roll a bunch of molecules around, flip an entire thing horizontally, you can just flip all the wedges and dashes. Now what's going to happen to our light? Well, enantiomers are going to interact oppositely. What is opposite of 23.1 degrees counterclockwise, but 23.1 degrees clockwise? So sometimes the optical rotation can be predicted. Now, if I just threw another random chiral molecule, we wouldn't be able to predict it from these two numbers. But if we know the number for the first molecule, it's always the opposite for the enantiomer. So enantiomers rotate plane polarized light in equal but opposite directions. Okay? In equal but opposite directions. So that's another property of enantiomers. Now this one's actually a little powerful because it allows us to measure and characterize and understand some properties of these enantiomers. Remember, otherwise enantiomers are, we can't really tell them apart, right? These molecules, okay, I mean, we could do a taste test and expose our bodies to them. No thanks. Let's measure some differences using some analytical equipment, using some science equipment. Well, this is a really interesting way because not only do we observe something that's special for the chiral molecules, but we observe something different, whether the molecules are one enantiomer or another enantiomer. Okay, so the optical rotation is the absolute degree of rotation. And it has signs. If it's positive, then it's a clockwise rotation. If it's negative, it's the counterclockwise rotation. Okay, so, and that's just, I mean, clockwise tends to be positive, looping around a circle. Counterclockwise is considered to be a negative degree rotation. So what you would see is that this molecule has an optical rotation, which is written as alpha which is equal to minus 23.1 degrees because it's a counterclockwise rotation. And if we drew the enantiomer, okay, so that's a mirror image of that structure. Or maybe you want to keep it in the same orientation, but just flip all of the wedges to dashes and vice versa. There's only one wedge, so we'll just flip it to a dash. Those two, the enantiomers, have an alpha equal to plus 23.1 degrees, and that's a clockwise rotation. So this is called, down here, this would be the positive enantiomer. And in fact, if we label this with an IUPAC name, we would put a plus sign in front of the IUPAC name. Now, similarly, this would be the negative enantiomer because it's just rotating things. It's rotating light in a negative direction. It's not negative because it's biologically introduces some negative effects necessarily. It's just the direction of the light, the direction of the light is rotated. Now, what we need to do is recognize, though, that the optical rotation, alpha as it stands, which is optical rotation, is an extensive property. Okay, what I was assuming about these two molecules as I presented them to you is that when you put them into the instrument to determine the extent to which light is rotated clockwise or counterclockwise, I assume that we use an identical instrument and we use the same amount of sample in both cells or in both instruments. Now, if we put more and more sample in, we're going to see greater and greater extents of rotation. So optical rotation is an extensive property. So what we have to recognize is that more sample is more rotation. Now, what I showed you actually was not the rotation, but it was the specific rotation. So minus 23.1 degrees and plus 23.1 degrees are actually, and by that I'm going to highlight these two. So minus 23.1 and plus 23.1, these are actually specific rotation values. So specific rotation is a new term, and specific rotation is our attempt to convert optical rotation into an intensive physical property. Now this is an intensive physical property. Now what we've done is we've just said that with specific rotation is we are going to set the amount of sample that you can use, okay? You can't have too much material. And if you do, you have to take it into account. And there's actually an equation. It's not overly complicated, but it's alpha divided by L times C. Okay, so this bracketed thing, this whole thing, that is specific rotation. So this equation says specific rotation is equal to alpha over L times C, where alpha is the observed rotation. So if you put some sample in there, some amount, whatever, like a bucket load, a pinch, whatever, it's the observed rotation, but you have to divide it by C, which is the concentration of the sample, and L, which is the path length of light. So it's a fairly simple equation. All it does is just takes into account the amount of sample that we have. So when I wrote plus 23.1 minus 23.1, that took into account the amount of the compound that we put in. And what's nice about this equation is it can be fixed or set for any amount of samples. So if we happen to have a gram, we put it in. It has to be a concentration, so it's a gram dissolved in some achiral liquid such that the concentration is like 1 gram per liter or something like that. We can take that into account, and we can convert any observed ratio back to 23.1 or plus or minus 23.1 for these particular compounds. Okay, so this is a characteristic property, and it's opposite for either enantiomers. So just to kind of summarize this a little bit, this compound has an alpha in brackets D equal to minus 23.1 degrees. Now the D just tells us standard conditions, which is sort of like room temperature conditions. It's not the same as STP if you have some chemistry background. And then the delta means adjusted for concentration, which we usually label concentration in brackets. And then similarly, if we had the enantiomer of this compound, the alpha D value would equal plus 23.1 degrees. Okay, so that is specific rotation and optical rotation. So kind of just what you would really want to know is the difference between specific and optical rotation and why specific rotation is useful. Specific rotation allows us to differentiate enantiomers. And we just use a plus or minus sign. So it allows us to label enantiomers. And labels are very pragmatic or practical, like what would you do if you had a vial of each enantiomer and you had to tell them apart. So we have label, but distinguish is a better word. Because remember, when you look at an organic molecule, you don't see a structure, a bond line structure. As fun as that would be, you see like a clear colorless liquid, a brown something, a white solid. You don't see the structure. So labeling would be helpful. Write a plus or minus on the label along with the name of the compound. It would allow you to distinguish the compound from everything else using the name, but then plus or minus to distinguish between it and its enantiomer, which looks very similar, but is subtly different due to the fact that they're stereoisomers. So we can distinguish and differentiate with plus or minus signs. Now we have that, but we also have a more classic approach to labeling enantiomers, and that is, I guess, just an alternative approach. And this has its roots deep into traditional and classic chemistry. So an alternative approach to labeling enantiomers is to call one another big word, dextrorotatory, or D, and then levorotatory, which is L. This has its roots deep into biochemistry and kind of classic biology. Turns out that if you understand optical rotation, even to the simplest degree, labeling each of these is very easy to do. That is, dextrorotatory molecules rotate light in the positive direction. So the rotate plane polarized light, I should be clear here, clockwise. So they rotate light clockwise. Okay, so this molecule, which had an alpha D equal to 23.1 degrees positive, is the D enantiomer. Okay, I know what you're thinking. Isn't it just easier to have a plus or minus sign if we're going to go to the trouble of measuring the optical rotation? Yeah, but this again it's just used. So I thought we should be aware of it, and we'll get to examples of when it is used. The alternative name is levorotatory. So levorotatory molecules rotate plane polarized light counterclockwise. Okay, so then continuing on, we have this example where the alpha D was equal to minus 23.1 degrees. That would then be the L enantiomer. The L enantiomer for levorotatory. Okay, so why do we need to know this? Most sugars are D enantiomers. Most amino acids, which build proteins, are L enantiomers. And that's just how our biology was built. And we'll look into more interesting aside on these topics of D and L enantiomers in the next module. So for example, glucose, the glucose that we know and love, which is sugar, is actually the D version. So we often see biochemists label this as D-glucose. And then if you wanted to get an amino acid, so I'll pick serine as one of my favorites. So I'm going to label serine as L-serine. Again, this is an amino acid. We use amino acids to build proteins. We use sugars or simple carbohydrates to build polysaccharides or polycarbohydrates, or excuse me, complex carbohydrates. So what this is, this D and this L, is a classic way of labeling molecules instead of using the plus or the minus. You would see this on a lot of chemical bottles. I want us to just be aware of the relationship of dextrorotatory and levorotatory to optical rotation as we go forward. So we spent a lot of time looking at how enantiomers are similar and how they can be labeled. In the next lecture, we'll look at some interesting consequences of enantiomers and how similar their structures are.